All right, so when it comes to algorithms, we are obsessed with the worst case scenario, right? How slow could this thing possibly get? But have you ever stopped to think, what if we flip that around? What's the absolute best an algorithm can do? Well, that question leads us to a really crucial concept, omega notation.
I mean, we pour so much energy into this, right? We use big O notation to map out the absolute slowest an algorithm can be, its upper bound. But what about the other end of the spectrum? Is there a guaranteed floor? A speed limit that it just can't go below no matter how perfect the input is?
Well, to answer that, we got to step outside our comfort zone of just thinking about the worst case. Because, not all algorithms are the same. Some of them have the secret weapon, a best-case scenario, where they just absolutely fly.
Okay, let's take a super classic example, insertion sort. Its whole job is to sort a list. You handed a list that's a total mess, completely random, and yeah, it's got a lot of work to do. But what if the list you give it is already sorted? It basically just zips right through it, confirms everything's in order, and it's done. That's its best case scenario.
And look, we're not talking about a tiny improvement here. This is huge. In its best case, insertion sort runs in linear time. That is worlds away from its worst case scenario, which is n squared. As your list gets bigger and bigger, the difference in speed is just astronomical. You literally can't ignore it. So that naturally leads to the big question, right? We've got big O for the ceiling, but what's our tool for the floor? How do we put a formal name and number to an algorithm's guaranteed minimum speed?
And that, my friends, is where omega notation comes in, with that cool-looking Greek letter. It's simple. If big O is the ceiling, think of omega as the floor. It's the official tool we use to talk about that asymptotic lower bound.
So here's the key takeaway, the big idea. When we say an algorithm's running time is omega of g of n, we are making a solid gold guarantee. We're saying that once your input gets big enough, no matter how perfect the data, how lucky you get, the algorithm will take at least this much time. It's the fundamental speed limit.
Okay, brace yourself for a second, because here comes the formal math. It looks a little scary, I know, but trust me, it's just a fancy way of saying what we just talked about. All it's really saying is, we can find some constant c and some starting point n0, where our function, our runtime, is always going to be above that floor, c times g of n. And this graph, this picture says it all. Everything in that math definition is right here. Once our input size n passes that n0 point, our runtime f of n is guaranteed to live on or above that line. Yeah, the runtime might bounce around a bit, but it will never, ever cross below that CGN line. That's the guarantee.
Okay, so now we've met big O, the ceiling, and omega, the floor. But they're not alone in the universe. They're part of a little family. And to get the full picture, we've got to meet the whole family.
And this little table right here is your cheat sheet. It makes it all super clear. Just think of it with these simple math analogies. Big O is kind of like less than or equal to. Omega is our greater than or equal to. And then there's theta, the Goldilocks of the group. It's not less than or greater than, it's just right. It's basically an equal sign for growth rates.
And this idea of a tight bound, this theta notation, is actually incredibly powerful. And you can probably guess where it comes from. It's all about the relationship between that ceiling, big O, and the floor, omega. And this theorem right here, this is the key that unlocks it all. It says, very formally, that you get a tight theta bound if and only if the upper bound and the lower bound are the same. In other words, when the ceiling and the floor are essentially the same thing, when they meet. And would you look at that? The graph proves it perfectly. This is what we call the sandwich theorem for a reason. The actual runtime f of n gets trapped or sandwiched between that floor and that ceiling. That means we know exactly how this algorithm is going to behave as the input grows. It's incredibly precise.
Okay, so that's the theory. But let's get real. Why does any of this actually matter? Why should you, sitting there about to write some code, actually care about a performance floor?
Well, for one, it's all about being precise with our language. Take a look at that first statement. The running time is at least O of n squared. That's just nonsense. Big O is an upper bound. Saying it's at least an upper bound is like saying the speed limit is at least 65 miles per hour. It doesn't tell you anything useful. But the second statement, now that is meaningful. Saying the worst case has a floor of n squared, that gives you a rock-solid guarantee.
But honestly, here's the biggest, most mind-blowing idea of all. Omega isn't just about one single algorithm. We can use it to talk about the built-in, inherent difficulty of an entire problem.
For sorting, it's been proven that any comparison-based sorting algorithm has a floor of omega n log n. So, if you come along and design a sorting algorithm that has a worst case, a ceiling of O(n log n, you've basically won. Your algorithm's ceiling matches the problem's floor. It is asymptotically optimal. You literally cannot do any better. How cool is that?
So, I'll leave you with one final thought to chew on. If we know for a fact that the problem of sorting has a performance floor of omega n log n, what should be going through your head when someone comes to you with a shiny new sorting algorithm and claims its performance is omega of n? What does that really tell you? Is it even possible? Something to think about. Thanks for joining me.